In this part of the video, I'm going to cover section 12.1, part 2, and this is going to get into significance test for the slope. So in this context, it's basically as you age, your skin gets droopy. So they measured people's age versus their ear height, and you're going to typically find longer ears in people who are older. Their ears aren't growing, it's just that the elasticity in their skin is breaking down. So they want to know, is there convincing evidence? That tells me this is a significance test. And after convincing evidence, that's the alternative hypothesis, because we always gather evidence for the alternative hypothesis. So that's going to help me on my state step. I'm going to start with defining the parameter. Beta is the true slope of the population, least squares regression line relating age to ear height. And for the parameter, we're going to assume there is no linear relationship, meaning the slope is 0. The question asked, is there evidence of a positive linear association? So the alternative would be that the slope is positive. We'll use our default level of significance of 5%. So there's a 5% chance that we make a type 1 error where the null is true, but we reject it. Plan. Here's the good news. Sometimes with these, they'll tell you the conditions are met. They've done that here, so I can go right to conditions met. We're going to do a one sample t-test for the slope. And the degrees of freedom here, they had 30 adults, minus 2 is 28. Moving on to the do step. So here's what I know in my sampling distribution. It's centered at that null value because we have a random sample, so it's unbiased. And our sample slope was 0.0021. I'm shading above because it's a upper tailed test. So when I calculate my test statistic, t with 28 degrees of freedom, it's going to be that sample slope minus the null claim that there is no relationship or the slope is 0, divided by the standard error of the slope. So just going back to the table, once you've identified the slope, we're really going to be looking at that row. And I have the coefficient and the standard error of the coefficient. When I divide these out, I get 0.3559. And what I want to do then is use that to calculate my p-value. So I'm going to go TCDF with that lower bound to infinity with 28 degrees of freedom. When I do that, I get a p-value of about 0.362. Now, what I want you to notice, if you follow this row over, under t, you get the same test statistic. So they're telling you the test statistic. P stands for p-value, but this is not the correct p-value. What I need you to recognize is this is always a two-sided p-value. So if this alternative was not equal to, this would be the correct value. So if I take that 0.7246 and divide it by 2, I did that just a minute ago, you'll notice that's where our p-value is coming from. Because this gives you the area in both the tails, divide that by 2, we need the area in one of the tails. That's where that 0.362 is coming from. So that's the do step. For the conclude, because our p-value of 0.362 is greater than our significance level of 0.05, we fail to reject the null. So we don't have convincing evidence that the true slope of the population, least squares regression line relating age and ear height is greater than 0. What kind of error could we have made? We could have made a type 2 error here. Why? Because it says fail 2. Type 2 error is when the alternative is true, but you fail to reject the null. So we didn't find convincing evidence that there was a positive linear relationship when in fact there was. They could ask you to interpret p-value in context. That would look like if the true slope of the population regression line relating age to ear height is 0, so if the null is true, there's a 0.362 probability of getting a sample result of 0.0021 or larger purely by chance. So on page 5, it's just a quick summary of the conditions that we covered, the confidence interval, the structure of that, the name, and then for the test, the structure of that, along with the name and the formula and the degrees of freedom. I mentioned this earlier in the lesson, I believe, but you still want to be able to interpret confidence level, type 1 and type 2 errors, p-value, and context. And this is just a summary of the confidence interval and the test. So what I would like you to do now is on the next 2 pages, you're going to find a confidence interval, you're going to find a test. I would like you to pause the video and work through the confidence interval, then come back, watch me go through that, then pause the video again, work through the test, come back, watch me go through that. All right. So here I am going through the confidence interval on page 6. Beta is the true slope of the population regression line relating the NEA change and the fat gain, non-exercise activity. For the plan, I do need to check the conditions. They've given me the scatter plot, the residual plot, and the histogram. So for the linear condition, the scatter plot is linear and the residual plot has no pattern. Independence 16 is less than 10% of all young adults. Normal, the histogram of the residuals shows no strong skewness or outliers. It is slightly skewed to the right, but that's okay. Equal standard deviation. I notice that in my residual plot, the residuals are pretty consistently varied. So I'd say the residual plot shows consistent variability. And then for the random condition, it was a random sample of 16. So the conditions are met. We're going to do a one sample. Oh, I left that out. One sample t-interval for the slope with degrees of freedom equal to 14. The 16 adults minus 2. Now I'm just going to take the table and use that. So this is the line for the slope. So there's the slope, there's the standard error of the slope, and you'll notice I use those here. Your slope plus or minus. The critical value comes from doing inverse t of 0.025 with 14 degrees of freedom times the standard error of the slope. And then when you add and subtract, you get about negative 0.005 to negative 0.001. The interpretation, we're 95% confident that the interval from that to that captures the true slope of the population regression line relating NEA change and fat gain. And I think I said it a little bit differently in my conclusion. Okay, let's move on to the last one, the test. So we're talking about truck price based on miles driven. So the more miles you drive, typically when you try to resell something, it's going to cost less when it comes to cars. So the state step beta is the true slope of the population regression line for miles driven and price. The null would be that there is no linear relationship, and the alternative would be that it's negative, because that's what they're asking. Is there convincing evidence? That tells you to do a test. And then what comes after that, that's going to be your alternative hypothesis. 5% level of significance. We're checking the conditions again. Scatter plot is linear, residual plot has no pattern. 16 is less than 10% of all used F-150s. The histogram of the residuals shows no strong skewness or outliers. The residual plot has consistent variability. It was a random sample of 16. So our conditions are met. We're going to do a one sample t-test for the slope. We have 14 degrees of freedom again, 16 trucks minus the 2. For the do step, we're going to take that sample slope, negative 0.16, minus the null value of 0, divided by the standard error of 0.03. I already know the test statistic is going to be negative 5.26. The p-value, even for a two-tailed test, is essentially 0 to 3 decimal places. So when I do TCDF from negative infinity to that negative 5.26, 14, I'm going to get something in scientific notation. It's very small. It's essentially 0. So for the conclusion, because the p-value is less than that, less than our significance level, we're rejecting the null. We do have convincing evidence that there's a negative linear association between the miles driven and the truck price. So more miles driven, in general, lower truck price. Because we're rejecting the null, this could be a type 1 error where we found convincing evidence of a negative linear association when in fact there was none. So that's it for the last lesson of the year. If you have questions, reach out to me. Hopefully that made sense.